7 people were kidnapped by a Mad Hatter. Yeah, I know it's happened before, but I can't help that it happened again. And this time's different, so it doesn't matter if you watched or didn't watch last time's kidnapping, it will still be fun to find out what happened this time. Blue and pink hats were once again placed on their heads, and they were asked to guess which hats they had on. They can't communicate with each other, and they can't see each other's guesses. This time, however, each person also has the option of not guessing. Now if even one person guesses incorrectly, or else if nobody guesses at all, then they fail, and something bad happens. On the other hand, if at least one person guesses correctly and nobody guesses wrong, the whole group is let free. In order to protect their identities, we refer to them as players 1 through 7, and we replace their pictures with hats. For instance, this is how we depict player 2 when we don't know what hat they have on. This is player 2 with a blue hat, and player 2 with a pink hat. Hello and welcome to Fine Design. Today's video is on a really nice hat puzzle that's easy to state and fun to think about. We will analyze it and get some hints as to what we are looking for in a solution. And we'll have to make quite the journey to another realm of mathematics to see this through. So let's start. Here's a clearer look at the situation. Persons 1 through 7, or players 1 through 7, have hats placed on their heads. Each hat is colored blue with probability half and pink with probability half. Each person can see everyone else's hats, but they cannot see their own hat color. Each player has a private slip of paper where they write their guess for the color of their own hat. The Mad Hatter looks at their slips and sees how many are right and how many are wrong. The players pass if there's at least one correct guess, and none of the guesses are wrong. The players are allowed to come up with a strategy before the hat placing starts, but cannot communicate after that. We want to know which strategy gives them the best chance of success. Let's start with a really simple strategy. Every player chooses their favorite hat color and guesses that. So here each player's slip has their favorite hat color on it. Player 1 likes blue, 2 and 3 like pink, and so on. In this case, some people have guessed wrong, and so they fail here. But there are many ways in which the Mad Hatter could have placed the hats. There are 2 to the 7 or 128 ways in which the Mad Hatter could have placed the hats. Let's call each of these a hat setting. In this new hat setting, there still are wrong guesses, so they fail this hat setting as well. And they would fail quite often. In fact, they would pass only in the unlikely case when the Mad Hatter happens to put everyone's favorite colors on their heads. This is, therefore, a bad strategy. And it makes sense that it's bad. With everyone guessing, it's really likely that somebody would guess wrong. So a more sensible strategy is for player 1 to guess, and for everyone else to choose not to guess. Now player 1 is correct half the time. Whenever player 1 is correct, they pass. Whenever player 1 is wrong, they fail. So now they pass in half the hat settings. That's much better. How would we get better than a half chance of winning anyway? Nobody knows their hat color, so everybody is wrong with probability half. It feels like that's the best you can do. Now let's try to phrase this argument more concretely. Here is how we're going to represent a strategy in detail, starting with the guess your favorite color strategy. This is a table with 7 rows and 128 columns. There are 128 different hat settings, and each one is represented by its own column. For instance, the shown hat setting is represented by the shown column. The entries of the column tell us whether the player's guesses are right or wrong for this hat setting when they follow this strategy. So here the first player guesses correctly, the second player guesses wrong, and so on. This table has all the information we could ask for. We can go through each column and see whether this strategy passes or fails the corresponding hat setting. As you can see here, and as we discussed, only 1 out of the 128 hat settings are passed. Now let's look at the strategy where only the first player guesses. As you would imagine, only the first row has correct or wrong guesses, none of the other rows have any guesses at all. And this strategy passes 64 out of the 128 cases. Now here's a strategy I randomly generated. We'll use this as an example to see what it means for a player to not have any idea about their hat color. Let's consider 2 columns that represent hat settings that are the same except for player 1's hat color. And let's look at player 1's performance in these 2 hat settings. To player 1, both of these hat settings look exactly the same because player 1 can't see their own hat color. So whatever strategy player 1 uses, it must have player 1 guessing the same in both of these hat settings. So if in one of these hat settings player 1's guess is correct, then in the other hat setting, player 1's guess is wrong. Similarly, here are two other hat settings that only differ in player 1's hat color. In one of the hat settings, the strategy told player 1 not to guess. So in the other hat setting also, the strategy told player 1 not to guess. The 128 hat settings get split into 64 such pairs. In each pair, player 1 either has one right guess and one wrong guess, or they have no guesses. The same is true for player 2, but the pairings are different because the pairings are going to be hat settings in which the only difference is player 2's hat. And this holds for all 7 players. One consequence of this is that each row has an equal number of correct and wrong guesses. And hence the whole table has an equal number of correct and wrong guesses. This doesn't yet tell us that 64 cases is the most you can pass, but it does tell us something. For instance, we can now conclude that no strategy can pass all 128 hat settings. This is because for each hat setting that is passed, you must have a correct guess in that column. So you need at least 128 correct guesses. But then there are also at least 128 wrong guesses. Each column that contains a wrong guess is a failed hat setting. So you have to have failed some hat settings. We just proved that we have to fail at least one hat setting. Can we prove something more? How many hat settings can we prove that we must fail? To pass the most hat settings, the best possible case would be something like this. Here we pass cases with exactly one correct guess, and fail cases by making all 7 guesses wrong. In this way, the wrong guesses bunch together, and they don't cover as many hat settings. We end up with 112 passed cases and 16 failed cases, which is incredibly good. The only problem is that this is not a valid strategy. None of the rows here have an equal number of correct and wrong guesses. We can fix that by shifting some guesses around, but it's still not a valid strategy because the wrong guesses and right guesses are not paired in the right way. The correct dot here is paired with this dot, so this guess should be wrong. But at least this gives us an idea of what we should look for. Our dream outcome would be to find a strategy that fails horribly in 16 hat settings, getting all the guesses wrong, and passes the 112 other hat settings, getting exactly one correct guess in each. Note that if it ever gets more than one correct guess in a single hat setting, it is doomed to fail more than 16 hat settings. As we chase this dream, the easier part for us to think about is how to get a strategy that gets all guesses wrong in a hat setting. So let's start with an arbitrary hat setting and try to get everything wrong here. I'm calling such a hat setting a red setting because that's how it will show up in the table for our strategy. To get this and only this setting wrong, player 1 could see whether the other hat colors that player 1 sees are consistent with red setting 1. And if so, player 1 could answer pink, because that would make player 1's guess wrong for red setting 1. Similarly, player 2 has a similar strategy they could follow, and so do all the other players. A more concise way to put this is that if a player sees hats consistent with red setting 1, the player answers inconsistently with red setting 1. The table for this strategy looks like this. That's a good start for us. We have a red column. Because of that, we naturally have some correct guesses in other columns. We still need 15 more red columns though, and obviously we can't choose a column to be a red column if it already has a correct guess in it. So we need to figure out which hat settings got a correct guess. We know how the pairing of correct and wrong guesses works. If we take the hat setting that differs from red setting 1 in only player 1's hat, player 1 has to have guessed correctly there. And we can create a similar hat setting for each player. Each of them has a correct guess. Let's call these 7 hat settings the neighbors of red setting 1. Neighbors because they differ in only one hat, and so they're the closest you can get to red setting 1. So this gives us our first hint when chasing our dream. It's impossible to have 2 red settings that are neighbors of each other, since every neighbor of a red setting has to have a correct guess. So when we choose our red setting number 2, let's choose a setting that is different from red setting 1 in 2 hats. Now the strategy of each player is to see whether the hats they see are consistent with any red setting. If so, they answer inconsistently with that red setting. A player cannot see hats that are simultaneously consistent with 2 red settings, because that would mean that the 2 red settings differ in only one hat, which we've avoided. Now how does this new strategy fare? We see that there are 2 red columns, which is awesome, but it looks like we have a problem. There's a column that has 2 correct guesses. We need to avoid that as well. So how did this happen, and how can we avoid it? If we look at which column has 2 correct guesses, it corresponds to this hat setting. This hat setting is a neighbor of red setting 1, differing in only hat number 4. It's also a neighbor of red setting 2, differing in only hat number 1. That's why it gets 2 correct guesses. So another thing we need to ensure is that 2 red settings should not share a neighbor. We say 2 settings are neighbors when they differ in exactly 1 hat. It's also easy to see that 2 settings share a neighbor only when they differ in exactly 2 hats. So what we want from our red settings is that any 2 red settings differ in at least 3 hats. And so we reach our solution for the hat puzzle. We need to choose red settings so that every new red setting we choose has at least 3 hats different from all previous red settings. I've written a program to find such hat settings for me. Once it reaches 16 such red settings, I will have achieved my dream strategy. And it's stuck. It found 9 red settings and now it's stuck because it can't find another hat setting that has at least 3 hats different from all of these. My dreams have come crashing down. But this video still has a lot of content, so maybe I shouldn't get dejected yet. The reason my program got stuck could be because it wasn't very clever in finding these 9 red settings. It maybe chose badly, and if it had chosen them with much more care, maybe it could have found more than 9. But how would we go about choosing these more carefully? And this is why I love this hat puzzle so much. We've done some cool analysis of a nice logical hat puzzle, tried making progress based on that, and now we're stuck at a question that looks nothing like the puzzle we started with. Now it is a more combinatorial question, but luckily for us, it's still a really neat and basic question. And even more luckily for us, because this is such a basic question, this has already popped up and has been studied in another branch of mathematics. So we'll take a detour now and do a quick introduction to error detecting and error correcting codes. I promise we'll be back at this question very soon. Error detecting and error correcting codes have a very simple backstory. Say you're trying to send a message to your friend via a signal of 7 bits. There are 128 different signals of 7 bits, so there are 128 different messages that you can send. So let's choose one of them and send it. But look, 1 bit got flipped while it was being sent. So now your friend thinks you sent them a message, but you didn't intend to send them that message. Now in this video, we'll be assuming that whenever you send a message, either no bit gets flipped or 1 bit gets flipped. So when I say error, I mean 1 bit flip. Error correcting codes do also deal with more bits getting flipped, but we won't get into that here. So how can we avoid this scenario? One way is to choose some special signals, which we call codewords. When you send a signal, you only attempt to send a codeword. Suppose a bit gets flipped again in the signal. Now your friend has received a signal, but the signal isn't any of the codewords. So your friend knows that a corruption has occurred and doesn't end up thinking that you sent them a message that you didn't intend to. The set of codewords is called a code, hence the name error detecting codes. Here our code has 64 codewords, so there are still 64 different messages you can send. 2 questions come to mind. How did we come up with this code that is able to detect if a bit flip has occurred? And can we find such a code with even more codewords? Clearly, the larger the code, the more useful it is. Let's answer the first question. And let's start with the codeword we sent. When you send this codeword and a bit gets flipped, there are 7 possible signals that it can result in. Since they're the closest you can be to codeword 1, we call them neighbors of codeword 1. We need to ensure that none of these neighbors are also a codeword in our code, because if one of them is a codeword, then your friend could have received it and would not have known that you didn't intend it. So for an error detecting code, the only rule we need to abide by is that no 2 codewords are neighbors of each other. Sounds familiar, right? Now let's go to the even cooler task of not just detecting that an error occurred, but fixing the error as well. Let's take 2 codewords that are different in 2 bits. Now if the signal your friend received is this one, there's a problem. Your friend can detect that a bit flip has occurred, but it's impossible to tell whether you were trying to send codeword 1 or codeword 2. This problem arises because the signal is a neighbor of codeword 1 and a neighbor of codeword 2. So it is impossible for your friend to correct the error. If instead you choose codewords so that no 2 of them share a neighbor, then any signal can be a neighbor of at most 1 codeword, and so you know that that codeword was the intended message. So when you are creating an error correcting code, you should also ensure that no two code words share a neighbor. And as I promised, we're back to exactly the same question. We want to know how many code words we can find so that any two code words differ in at least 3 bits. But wait, if we're back to exactly the same question, how was any of this useful? The answer to that is that by viewing it from a new perspective, we can now think in ways that we would not have thought earlier. After all, error correction is clearly more intuitive to think about than something like ways of coloring hats such that no two ways share a neighbor. Error detection and correction have been important and in use for many decades now, with the parity check bit being popular since the advent of digital data storage. The idea is really straightforward. If you have 7 bits and you want to be able to tell if a bit flip has occurred, then limit yourself to 6-bit messages. Leave the last bit as a parity check bit. We count how many ones there are in our message. If it is even, we put a 0 in the parity check bit, and if it is odd, we put a 1. Now suppose one of the message bits gets flipped. This will change the count of the ones in the message by 1. So it changes the parity, and our parity check bit will be wrong. If instead the parity check bit gets flipped, then since the message is still the same, the parity check bit is again wrong. So if any bit flip has occurred, our parity check bit will be wrong, and so we can detect the error by looking at it. With this observation, we can create an error detecting code. We write down all possible messages that are 6 bits long. Then we add the parity check bit. All these 7-bit signals have the correct parity check bit. So if you send me one of them and a bit gets flipped, I can detect that an error occurred. We've created an error detecting code, and from our discussion earlier, this means that no two of these are neighbors of each other. Our perspective switch seems to be working out well. Around the year 1950, Richard Hamming asked why it was that computers could detect an error but could not correct it. And he came up with a very clever use of parity checks. Consider this table with 16 message bits. Each column has a blank space for a parity check bit. We fill each one with the parity of the message bits in that column. Similarly, each row has a blank parity check bit that is filled with the parity of the message bits in that row. Now let's see what happens when a bit gets flipped. If the bit is one of the column parity check bits, it doesn't affect any other parity, and so only that parity will be wrong. A similar thing happens if one of the row parity check bits gets flipped. If a message bit gets flipped, that affects the parities of both its row and its column. So those two parity check bits will be wrong, and nothing else is affected. So now if I get a message, and I look at which parity checks are wrong, I can figure out what happened. If none are wrong, there was no error. If only one column parity check or only one row parity check was wrong, then that parity check bit was the one that got flipped. If, like in our case here, both a row and a column parity check are wrong, then the bit that got flipped was the message bit in that row and column. With this clever construction, we're able to figure out which bit got flipped and correct it. These 24 bits can be viewed as a 24-bit signal. We can again create a code by writing down all 2 to the 16 possible messages and filling out the parity check bits. And since this is an error correcting code, we know that no two of these code words share a neighbor. This perspective switch was really useful. So let's now apply it to a scenario with 7 bits. We can do that with a table like this. It has 3 message bits and 4 parity check bits. So this gives us a code with 8 code words. Wait, that's not good. My program gave me 9 red settings. This approach is only giving me 8. Is there a better code than this one? In fact, the 9 red settings my program gave would be an error correcting code with 9 code words. So clearly better codes do exist. And Richard Hamming realized this as well. He saw that although the table structure was useful to figure out which bit got flipped, there was a more fundamental reason it worked. Let's go back to the earlier table and let's number the parity checks. There are 8 of them numbered from 1 through 8. And each message bit is labeled with which parity checks it is involved in. When we saw 2 wrong parity checks, we knew the flipped bit was in that row and column. But now, even if it isn't arranged in a table, we can figure out the flipped bit. Parity checks 4 and 7 are wrong, and so the only bit that could have caused this is the bit labeled 4,7. All that we needed was that every bit has a different label, so that the wrong parity checks can uniquely identify the bit. With this new interpretation, we can add more than 200 new message bits without increasing the number of parity check bits, since there are so many labels that weren't used previously. Now when we want to enter the value of parity check 1, we have to take the parity of all message bits that have a 1 in their label. And similarly for the other parity check bits. Now if we get a message and we see that parity checks 1, 5, 7, and 8 are wrong, we immediately know that the bit that got flipped was the one with the label 1, 5, 7, 8. This is a much more efficient use of the parity check bits. And to top it off, we can now use just 3 parity check bits with 4 message bits. By writing down all 16 messages and then adding the parity check bits for each, we get an error correcting code with 16 code words. Our dream has come true. Take each code word, think of the 7 bits as 7 hats. Each 0 is a blue hat and each 1 is a pink hat. And here we have 16 hat settings with no 2 hat settings being neighbors and no 2 hat settings sharing a neighbor. These can be our red settings. Each player looks to see if the hats they see are consistent with any of these settings. If so, they answer inconsistently with that setting. The strategy results in this table, with 16 red columns, and all the other 112 columns having exactly 1 correct guess in each. We just found the strategy we dreamed of. And that's it for this puzzle. We'll conclude this video with a small discussion on error correcting codes. In the description below, I've linked to the paper in which Richard Hamming introduced error correcting codes. It has a wonderful introduction that gives you a glimpse into how information was being handled 70 years ago. He also talks about correcting more than one bit flip, the basics of which I can show you right now. It's best described using the notion of Hamming balls. A Hamming ball of radius 1 around a signal is just the signal and its neighbors. A Hamming ball of radius 2 would include the signal, its neighbors, and their neighbors as well. If you think of the distance between signals as being the number of bits that they differ in, then the word ball makes sense here. The center is the signal, and we're including everything that's a small distance away from it. Using this, we can tell exactly when a code can detect k-bit flips. It's basically when the Hamming balls of radius k around the codewords don't contain other codewords. Because then even if there's an error of k-bit flips, the resulting signal cannot become a different codeword. Similarly, we can tell exactly when a code can correct an error of k-bit flips. That would be when the Hamming balls of radius k around the codewords don't overlap. Because then even if there's an error of k-bit flips, the resulting signal will still be in the Hamming ball around the intended codeword, and not in the Hamming balls of any of the other codewords. And even though we changed our perspective away from this notion of distance, moving back to it is also a useful perspective switch. Now you can make statements like, the number of codewords times the size of each Hamming ball should be at most the number of possible signals since the Hamming balls don't overlap. This tells you that you can't have too many codewords, and it is called the Hamming bound. There's also the Gilbert-Varshamov bound that says that you can always find a certain number of codewords, and that also uses the volume of Hamming balls in its analysis. These are some of the basic results in the field of coding theory, a vast and fascinating field. Now there are 2 videos of mine that are relevant to mention here. One is about COVID testing, and it's a very interesting application of error correcting codes. One reason to watch it is that it uses a very nice connection to polynomials instead of using parity checks like we did in this video. The other video is another hat puzzle. That one doesn't go to another field of mathematics like this video did, but it does a very beautiful and intricate coordination of guesses, and you should definitely check it out for that. That's all from me for now. Goodbye, and have a great day.